Okay, so back here, and now we're going to talk about mathematical direct proofs. And this is, I believe, question 8 in your homeworks. So 8 or 9 or something like that. Or this is half of it. So we're going to prove these using De Morgan's laws, or we're going to prove De Morgan's laws directly using that method of choice. So as a reminder, first we have to show that this guy is a subset of this guy, and then we have to show that this guy is a subset of this guy. So first, we wish to show that A intersect B complement is a subset of A complement union B complement. How are we going to do this? We're going to pick an arbitrary x in A intersect B complement, and we're going to show that that x is in here, is in A complement union B complement. So if pick x in A intersect B complement, therefore x is not an element of A intersect B. Therefore, x is either not an element of A, or x is not an element of B. If x is not an element of A, then x would be an element of A complement union, or then x would be an element of A complement, and therefore x would be an element of A complement union B complement, right? We're only adding extra stuff. If x is an element of B, then it follows the exact same structure. Complement, and therefore this second line right here, you don't have to write it. You could just say by symmetry, if x is an element of B, then if x is not an element of B, then x is an element of A complement union B complement. Symmetry just means that the same exact argument follows for x is not an element of B as you just showed for x is not an element of A. Just means that the argument is the exact same. So we just showed that, therefore, because this is an arbitrary element of this guy, it's also in this guy, we have just showed that A intersect B complement is a subset of A complement union B complement. Now we want to show A complement union B complement is a subset of A intersect B complement, right? So A complement union B complement. If x is an element of A complement union B complement, then x is an element of A complement, or x is an element of B complement. If x is an element of A complement, then x is not an element of A. Therefore, x is not an element of A intersect B, right? Because it would have to be in both A and B. Therefore, sorry, this should be not an element. Therefore, X is an element of A intersect B complement. Now, a symmetrical argument shows if X is an element of B complement, then X is an element of A intersect B complement. Therefore, A complement union B complement is a subset of A intersect B complement. Therefore, A complement union B complement is equal to A intersect B complement. But these sets are the same because we have just shown that they're subsets of each other. And now you've got a few different options to mark that a proof is done. Actually, we should put that therefore there. One is you can put in a box right here. Another is you can just put QED. QED stands for Quod Erat Demonstratum, basically, which is what we were trying to prove in Latin. Got a few more options here to prove, a few more statements to prove. The sum of two even integers is even. So any even integer can be written as 2 times k for some k. So for some integer k. So k is in the integers. Right? So the sum of two even integers, we would have 2k plus 2j. That would be equal to 2k plus j. K and j are both, comma, j are both integers right here. And this is just by commutativity, distributivity, the distribution property. And this right here is going to be equal to some integer L in the integers, or some L in the integers. Therefore, the sum two even integers can be written as 2L for some L in Z. Therefore, it is even. Similarly, the sum of two odd integers is odd. Any odd integer can be written as 2k plus 1 for some k in Z. This is just the definition of an odd integer. This is odd integer can be written. Therefore, the sum of two odd integers can be written two k plus 1 plus 2j plus 1. And that's going to be equal to 2k plus 2j plus 2. So that's going to be equal to 2 times k plus j plus 1. This guy right here, the sum of 3 integers is going to be an integer, can be written as L in the integers. Therefore, we have the sum of 2 odd integers can be written as in the form L, Z, or it is even. So another classic example, something that you've probably seen a ton of times in high school, but have never actually seen a justification for why, is the Pythagorean theorem. So as a reminder, the Pythagorean theorem states, so what we're trying to show is the squares of the two shorter sides of a right triangle. And we'll normally write these guys as A and B, is equal to the squares of the lengths, to the square of the length of the hypotenuse. And we normally write that as C. To get A squared plus B squared is equal to C squared. So how are we going to do this? First, we're going to examine start putting this here. Examine a square of side length A plus B. So right here, perfect square, absolutely flawless. Just give you guys a visual aid. Cool. This square can be goes into 4 right triangles with legs A and B and an inner square. So what do we get? So this inner square, and we really should prove actually that that this guy on the inside is a square. So first off, all the sides are the same length, and then we have this guy is the same as this guy, and then this guy is going to be the same as this guy because these triangles are all the same. But I'm not going to focus too much on that. And therefore, this guy plus this guy plus this guy is going to be equal to 180 degrees. And this guy plus this guy plus this guy is also going to be equal to 180 degrees. So this is a right angle. We're not actually using that level of rigor, so I'm not going to write that out. But to show that this guy on the inside is actually a square, you would have to do those steps, write those steps out. So, little exercise, fill in the blanks. So this and an inner square. Cool. So now want to find the area of the big square. Find the area of that big square. Now, in order to do that, we've got the most basic method is we know that the length of each side is a plus b. So the area will be equal to a plus b squared. So that's going to be a squared plus 2ab plus b squared. But a is also equal to the sum of areas of constituent parts. Therefore, a is going to be equal to c squared, that's the area of this inner square, plus 4 times 1/2 AB. So this is the area of the triangle, and we've got 4 of those triangles, and that's going to be equal to c squared plus 2ab. Therefore, c squared plus 2ab is equal to a squared plus b squared plus 2ab. Just rearrange this guy right here. And now subtract 2ab from both sides. C squared is equal to a squared plus b squared. And these were just the names that we gave to the lengths of the sides of the hypotenuse. Therefore, we have proven our statement.